Hello, I'm Associate Professor Ben Holken. I'm from UTS. I'm in the School of Mechanical and Mechatronic Engineering, and we're in our Dynamics Lab here today. It's another video on rotating machinery vibration, and in particular, in this case, we've got a rig here that's been set up to allow us to look at bearing fault frequencies. This is a very important topic. Bearings are in many rotating machines, and we can measure vibration signals from machines and use the information in those vibration signals to be able to predict bearing faults and understand how bearings are failing in service, and then schedule repairs to those systems to allow us to be able to keep machines running without unplanned downtime to be able to repair catastrophic failures. If you come in here and have a little bit of a closer look, I'll explain the setup that we have here. So we have a rig here with a motor, a digital motor connected to a shaft with a gear on with 29 teeth. There's a flexible coupling between the motor and the shaft, and these are straight cut gears, so as I rock this backwards and forwards you can hear there's some noise, there's some backlash between the gears, obviously needs to be some clearance in here, and these gears are in a ratio of 29 to 20 teeth, and then this driven shaft here is connected to an eddy current brake system here, which we can use to apply some load to this driven shaft system. And then we have a 48 to 24 tooth, 2-to-1 ratio belt drive with a toothed belt that's connected to another shaft here. And on this shaft we have an axially loaded bearing with a deliberately introduced fault in it. And we are measuring the vibration of the bearing housing with this accelerometer, which is connected to our acquisition system to be able to determine the nature of the fault. We have another accelerometer mounted to this shaft housing over here, and these accelerometers are both charge-based accelerometers, charge mode accelerometers, and the signal conditioning is provided for them with our inline charge converters that are IEP powered via this end to the acquisition system, and this end's connected to the accelerometer. We have two of those in line with the cabling that's connected to the acquisition system. We're using a National Instruments 9234 input module. It's a 4-channel voltage input module for our analog channels. It provides the IEP signal conditioning. So we have, in addition to the tacho, which I've not actually mentioned yet, this is the tachometer here. This measures the once per rev speed of the shaft. So there's a piece of tape on the shaft here, and as the shaft rotates, the tacho sees the tape and we get a red light, and it also provides an output to the acquisition system. I can also, if I close the lid here, it's going to be a little bit quieter when I run it. I can start the motor running at, say, 200 RPM using this software that we've produced at UTS. I have a handheld tachometer in my left hand here. This is another laser source. We can turn the tachometer on and we can measure the frequency. It's upside down, unfortunately, but it's 200 RPM for this shaft. I've got another piece of tape over here, so this is our 29 to 20, so that's 290 RPM. 1.45 times the shaft speed here, and then this shaft over here is rotating at 2.9 times the shaft speed, so 580 RPM. That's a handheld tachometer. I've shown some other types of instrumentation for rotating machinery measurements, particularly for shaft speed measurements, in a previous video. In this video, we'll now increase the speed up to 400 RPM, which is going to be 1160 RPM on the shaft with the faulty bearing in it. I'll restart the spectral averaging on the software, and I'll explain what's happening in the software here. So on this trace we have in the time domain the tacho pulse train from the tachometer, the red curve, so we get high, low, each time the piece of tape passes. And that allows us to extract a measurement of the actual RPM. Remember, this is the motor speed, which is 400 RPM, but the shaft that's got the dodgy bearing on is rotating at 1160 RPM, and that is equivalent to 19.3 Hertz. This is our measured shaft frequency down here, which updates every time I restart the spectral averaging. so 19.5 hertz. This is the accelerometer signal, the white curve in here in time domain, and this is a very busy signal. There's lots of information in here, and in this signal information is included that relates to the damage on the bearing. This is a power spectrum from the same signal. So I also have a cursor, 3 cursors on here which I can move, and they're linked together. There's a cursor at a fundamental frequency and a first and a second harmonic. So these are multiples of the fundamental frequency. As I scroll and increase the frequency of the fundamental, this one is at 2 times and 3 times the fundamental frequency, and the display down here gives me the frequencies at which those cursors, those linked cursors, are positioned on the spectrum. So if I move this to this biggest peak here, this large peak here, we've got half hertz resolution. The first order cursor is at 19.5 hertz. That coincides with the shaft frequency. But there are some other components in this spectrum. In particular, there's a component at approximately 76, 77 hertz. And this is related to the bearing damage in this system, and there's also a first harmonic over here. Based on the shaft frequency, this software also calculates for me the various bearing fault frequencies, the fundamental train frequency at 7.3 hertz, the bearing pass frequency on the outer race at 73 hertz, 73.5 hertz, inner race 118, and the ball spin frequency 38.7 hertz. These are functions of the shaft speed as well as the properties of the bearing. We defined the properties of the bearing in the previous sheet. Here are the frequencies from the various local faults. These are the equations that are being used based on these input parameters and the measurement of the actual RPM to determine these frequencies. And we can use these frequencies to help us interpret that this peak, which is at approximately 76 hertz, and its harmonic multiples, first and second harmonics at 2 times and 3 times, are clearly related to some bearing ball pass frequency on the outer race, which is around about 74 hertz. And that's how we use this kind of equipment to help demonstrate how we can use vibration analysis to diagnose challenges, problems, faults with bearings and rotating equipment. I've been Ben Holcomb, this is UTS Tech Lab. Thank you very much for watching.